Okay, in this video, we're going to be looking at the operation of decimals on decimals. Here we're going to be multiplying decimals. We're going to look at scientific notation, also dividing decimals, mental computation, rounding decimals, estimating decimal computations using rounding, and also we're going to look at round-off errors. All right, first of all, we'll talk about how to add decimals here. We're going to add 2.16 and 1.73. Here they're using a concrete model for this one. In this case here we're using two flats to represent the 2, or the whole number 2, and then the long will represent 1/10, and then your 6 unit cubes will represent 600ths. And then for 1.73 we have 1 flat for 1 whole, 7 longs for the 7/10ths, and then 3 unit cubes for the 300ths. Add these together, you'll have 3 flats, and then 8 longs and 9 unit cubes. That represents 3 89/100ths, or 3.89. We can change the problem to one we already know how to solve. That is the sum of involving fractions. In this case here, 2.16 or 2 1600ths will be 2 plus 1/10 plus 6/100 if we were to write this in expanded notation. The same with 1.73. That'd be 1 plus the 7s in the tens place, that's 7 over 10, plus 3's in the hundreds place, 3/100. And then add the whole numbers together, like 2 plus 1, that's 3. Then you got 1/10 and 7/10. Those are your like fractions, so that's 8/10. Then 6/100 plus 3/100. Those again are like fractions. Add those, you get 9/100. So here, if we were to write that as a decimal, that would be 3 89/100ths, or 3.89. Okay, look at multiplying decimals. If there are n digits to the right of the decimal point in one number, and m digits to the right of the decimal point in the second number, multiply the two numbers, ignoring the decimals, and then place the decimal point so that there are m plus n digits to the right of the decimal point in the product. In other words, you'll multiply the numbers as you would normally do if you were multiplying whole numbers. But then you're going to count the number of decimal places to the right of both of those factors. That sum is going to be the number of decimal places in the entire product. Let's say we want to compute each of the following, like in part A, 6.2 times 1.43. In 1.43, there are 2 numbers to the right of the decimal point. In 6.2, there's only 1 number to the right of the decimal point. Add 2 digits and 1 digit, you're going to get 3 digits. So that means the final answer will have 3 numbers to the right of the decimal point. And we multiply as we normally would, you'll get 8866, but we have to have 3 numbers to the right of the decimal point, so the decimal point will be right after the very first 8, so it'll be 8.866. Part B, you got 0.02 times 0.013. Well, 13 times 2 will give you 26, but in this case, there are 2 numbers to the right of the decimal point in 0.02 and 3 numbers to the right of the decimal point in 0.013. 2 plus 3, that's 5. The final answer must have 5 numbers to the right of the decimal point. So in other words, we need to put 3 zeros in front of it, in front of the 26, and then put your decimal point there. That way you'll have 5 numbers to the right of the decimal point, which will be 0.00026. And 1,000 times 3.6. Notice that we're multiplying by a power of 10. But still, 3.6 times 1,000 will give you 3,600.0. Keep in mind, 1 number to the right of the decimal point means we need 1 number to the right of the decimal point in our final answer. Now this brings up the concept of what we call scientific notation. Scientists use scientific notation to handle either very large or very small numbers. For example, the distance light travels in 1 year is 5,872,000,000,000 miles, and that's called the light year. We can rewrite this as 5.872 times 10 to the 12th. And also, for a very small number like this one, the mass of an electron is 0.000547875 atomic mass units. We can express that as 5.4875 times 10 to the negative 4 power. Okay, so here's the definition of scientific notation. In scientific notation, a positive number is written as a product of a number greater than or equal to 1 and less than 10 and an integer power of 10. To write a negative number in scientific notation, you treat the number as a positive number and join the negative sign in front of the result. Now let's look at some examples here. Let's say we want to write 413,682,000 as a number in scientific notation. And actually, I'm going to work through these ones with you. So in this case here, we got 413,682,000. Now, the way you're going to write that in scientific notation is this. You want to place a decimal point behind the very first non-zero number in this number. You want to put the decimal point behind the 4. Okay? So that means you're going to have 4.13682. And we're going to disregard the zeros here when we write this as a decimal. And it's going to be multiplied by 10 to some power. Now let's look at this number. If we're going to place the decimal point behind the 4, count how many numbers that are immediately after that. So it'll be 1, 2, 3, 4, 5, 6, 7, 8. The 8 numbers after this decimal point, that's going to represent your power of 10. So this is written as 4.13682 times 10 to the power of 8. Okay, the next one is 0.0000231. And we want to write this in scientific notation. This one is a decimal. Okay? So here, we want to place the decimal point behind the first non-zero number that we see, which is a 2. So the decimal point will be behind the 2. So it'll be 2.31, and it's going to be multiplied by 10. Now, since it's a decimal, the power of 10 will be negative. If it was a whole number like this one, your power of 10 would be positive. But since it was a decimal here to begin with, our power of 10 is going to be negative. Now, how many decimal places, how many numbers are there from this decimal point to the decimal point that we place behind this 2? 1, 2, 3, 4, 5. So it'll be 10 to the negative 5th power. So 0.0000231 would be 2.31 times 10 to the negative 5th. All right, the next one is 83.7. Now this number is not written in scientific notation because the number must be at least 1 but less than 10. This one is bigger than 10. So what we're going to need to do here, we need to place a decimal point behind that 8. So it'll be 8.37 times 10. Now how many decimal places, how many numbers are there between this decimal point and the one that we put behind the 8? Only 1. So it'll be 8.37 times 10 to the first power. And then part D, negative 10 million. Okay, here we need to place a decimal point behind the first non-zero number, which is a 1. So here we're going to bring over -1 times 10. Now if we place the decimal point behind the 1, how many numbers are there behind it? There's 7. So it's -1 times 10 to the 7th power. Okay, that's how we convert each whole number into a number in scientific notation. Okay, now this one we're going to convert to standard numbers. It's already written in scientific notation. You just want to convert those into standard form. Like this one, 6.84 times 10 to the -5th. 6.84 times 10 to the -5th. Now, your exponent for 10 will tell you how many places you need to move either to the left or to the right. If your exponent is negative like this one, you're going to move the decimal point to the left. If it's positive, then you'll move the decimal point to the right. In this case, our 5, we have -5, so we need to move this decimal point 1, 2, 3, 4, 5 places to the left. Which means we need to put 4 zeros in front of it. So this will be 0.00000684. That will be the actual number in standard form for 6.84 times 10 to the -5th. Okay, the next one is 3.12 times 10 to the 7th. Now here the exponent for 10 is a positive 7. That tells me I need to move this decimal point in 3.12 7 places to the right. So here I'm going to go 1, 2, 3, 4, 5, 6, 7. That means I need to put 5 zeros behind the 2. So in other words, this will be 312 with 5 zeros, which means this will be 31,200,000, which is a standard number for 3.12 times 10 to the 10 to the 7th. Okay, and then finally negative, and in parentheses 4.08 times 10 to the 4th. Now we know our answer is going to be negative, okay? But the 4 in 10 to the 4th is positive. So in 4.08, I need to move the decimal point to the right 4 places. So here, we're going to go 1, 2, 3, 4 places to the right. I need 2 zeros there, so this will be 40,800. And it will be negative 40,800 as my answer to the opposite of 4.08 times 10 to the 4th. Okay. Some calculators have the double E key, which can be used to represent numbers in scientific notation. So, if we want to find 5.2 times 10 to the 16 times 9.37 times 10 to the 4th, these are the keys that you'll have to press. Okay, using that double E button. And it all depends upon what type of calculator that you have. Okay. Let's look at dividing decimals. Let's say we want to divide 128.6 by 4. Okay, 128.6 divided by 4. If we were to write this as this, 12,860 divided by 100, divided by 4 over 1, and of course we multiply by the reciprocal of 4 over 1 if we want to, saying 12,860 over 4 times 1 over 100 would get 3215 times 1 over 100, which will be 32.15. And in some cases, you can use long division in order to divide decimals, like in this particular illustration here. When the divisor is a whole number, the division can be handled as with whole numbers. The decimal point can be placed directly above the decimal point in the dividend. And this is the way that they divided the decimals using long division. Here you place the decimal point directly above the 1 in the dividend in your quotient. And just divide as you would with whole numbers. Okay? But when the divisor is not a whole number, as in 1.2032 or 0.32, we can obtain a whole number divisor by expressing the quotient as a fraction, and then multiplying the numerator and denominator of the fraction by 100. This corresponds to rewriting the problem in Form A as an equivalent problem in Form B as follows. So in this case here we got 1.2032 divided by 0.32. What they did was they moved the decimal point 2 places in the divisor so that this will become a whole number. Well, if we move the decimal point 2 places in the divisor, we need to move the decimal point 2 places to the right in the dividend as well. So it'll end up being 120.32 divided by 32. And in elementary school tests, this process is usually described as moving the decimal point 2 places to the right in both the dividend and the divisor, or multiplying the divisor and dividend by 100. So in other words, the objective here is if your divisor is a decimal, you want to move the decimal point, how many places you're going to need to move to the right in order for it to be a whole number. And you have to move that decimal point the same number of places to the right in your dividend as well. Okay, now here we're going to look at mental computation. Some tools for doing mental computations with whole numbers can be used for decimal numbers, like if we have 1.5 plus 3.7 plus 4.48. We can use the breaking and bridging method to add these two decimals, like 1.5 plus 3 would give us the 4.5, and then you got 0.7 plus 0.448. Add 4.5 and 0.7, you're going to get 5.2. Then 5.2 plus 4, that's 9.2, and then 9.2 plus 0.48 would be 9.68. That's the final answer, using the breaking and the bridging approach. Also, compatible numbers can be used. Here, decimal numbers are compatible when their sum is a whole number, like 7.91, 3.85, 4.09, and 0.15. We're adding those 4 decimals together. The compatible numbers will be 7.91 and 4.09 because those two numbers add up to 12. Also 3.85 plus 0.15, that's another pair of compatible numbers. Those two add up to 4. So now add 12 and 4 together, you'll get 16 as your final answer. And also we can make compatible numbers here, like 9.27 plus 3.79. We can break 9.27 up as 9.25 plus 0.02 and 3.79 as 3.75 plus 0.04. Here, 9.25 and 3.75 are compatible numbers. Those add up to 13. And then we got 0.02 times 0.04, that would give us 0.06. 13 plus 0.06 would give us 13.06 as the final answer. The other method would be balancing with decimals in subtraction. Here we got 4.63 minus 1.97. I'm going to make 1.97 a whole number by adding 0.03 to it. If I do that to the subtrahend, I must do that to the minuend as well. Add 0.03 to the 4.63. Well, 4.63 plus 0.03 will give me 4.66. 1.97 plus 0.03 will give me 2. 4.66 minus 2, that's simply 2.66. See, that's also an easier way of doing a mental computation. And also, balancing with decimals in division is another way for mental computation. 0.25 divided into 8. Let's multiply the dividend and the divisor by 4. Because here 0.25 times 4 would give me 1. 8 times 4 would give me 32. So now I have a compatible division problem. 32 divided by 1. That's simply 32. Rounding decimals can be done on some calculators using the fix key. To round the number 2.3689 to thousands, you'll enter fix and then 3. And it depends upon what calculator that you have. And the display will show 0.000 because it's going to show 3 numbers after the decimal point. Then you're going to enter the number 2.3669 and then press the equal key. And the display will give you just this, 2.367. And the reason for why it shows that because of this. The number in the thousands place is a 6. The digit after that is a 9. 9 is bigger than 5, so we increase that number by 1. So it'll be 2.367 to the nearest thousandth. Now let's look at these numbers here. We want to round each of the following numbers here, like 7.456 to the nearest hundredth. Okay, in 7.456, the number in the hundredths place is a 5. The digit to the right of that is 6. That 6 is less than 5, so we increase this 5 by 1. So it'll be 7.46. And we drop off the rest of the numbers to the right of it that we're rounding off to. 7.456 to the nearest tenth. The number in the tenths place is a 4. Next to it is a 5. It does equal to 5, so the 4 will increase by 1. So it'll be 7.5. And all the numbers again to the right of the tens place will be dropped off. So it'll be 7.5. To the nearest unit, or sometimes the nearest whole number. We look at the ones place, the number immediately in front of the decimal point. That's the 7. Next to it is a 4. That 4 is less than 5, so the 7 remains the same, and everything else is dropped off completely. So this 7.456 to the nearest unit would be 7. Now, 7,456 to the nearest thousand. In the thousands place is a 7. Next to it is a 4. That 4 is less than 5, so the 7 remains the same. But since we're dealing with the thousands place, we change the numbers to the right of it to zeros. So it'll be 7,000. And then 745 to the nearest 10. The number in the tens place is a 4. To the right of it is a 5. It is equal to 5, so this 4 will increase to a 5. And this 5 will change to 0, so it'll be 750. And then 74.56 to the nearest 10. That 7 is in the tens place. To the right of it is 4. The 4 is less than 5, so this 7 remains the same. This 4 will change to a 0. All the numbers after the decimal point will drop off, so it'll be 70 as your answer. Rounded numbers can be useful for estimating answers to computations. When computations are performed with rounded numbers, the results may be significantly different from the actual answer. Other estimation strategies, such as front-end clustering and grouping to nice numbers that were investigated with whole numbers, will also work with decimals. Round-off errors are typically compounded when computations are involved. When computations are done with approximate numbers, the final result should not be reported using more decimal places than the number used, with the fewest decimal places. That is, an answer can be no more accurate than the least accurate number used to find it. Okay? And here's some things that you need to know when you're dealing with round-off errors. Non-zero digits are significant. So here they talk about significant digits here in this case. Non-zero digits like 1 through 9 are always significant. Zeros before other digits are non-significant. So let's say 0.0016. These two zeros are non-significant. Zeros between other non-zero digits are significant. So let's say 0.1015. This zero is significant because it's between non-zero digits. Zeros to the right of the decimal point are significant. Like 48.50. That zero that's after the 5 is significant. And to avoid uncertainty, zeros at the end of a number are significant only if to the right of a decimal point. Okay? Here is significant because it is to the right of a decimal point. Okay? So that's the rule for significant digits. And that will conclude this particular section on operations on decimals.